Hello, this is a video on two-dimensional boundary value problems using direct methods. So the problem we're going to look at is the heat diffusion in a two-dimensional slab, as shown in this figure, where I have x and y coordinates, and here's my slab. The differential equation governing the behavior of or the distribution of the temperature within this two-dimensional slab is the Poisson equation, where we have the second derivative of temperature with respect to x and y equal to 0. The boundary conditions we have are along the four boundaries. These two edges, like fourth and in the north and east side, the temperature is 25, and the west and south side is 50 degrees. And to make it very generic, I set the domain length along the x from 0 to 1/2, and along the y from 0 to 1/2. So the boundary conditions can be written this way, that at x equal 1/2 for all y means this is x equal 1/2 for all y, the temperature is 25. And so this boundary is for all x at y equal 1/2 is 25 right there. This thing is at x equal, okay, so the west edge is at x equals 0 for all y, temperature is 50. And the bottom side, the temperature at x equal, for all x and y equals 0, the temperature is 50. Alright, so here are the boundary conditions. The way we do this is we use central difference. We're going to use central difference for each term. For the first term, we apply the central difference. Now note that because we have two spatial coordinates x and y, we have two indices, I and j. So think of I as the index for x and j the index for y. So then when I talk about Tij means temperature at x equal xi and y equal yj. Alright, so given that, we can discretize the first term using central difference. So it's going to be the temperature at the previous x, so Ti minus 1, and j is fixed, minus 2 times the temperature at the current point, which is Tij at point I, and then the temperature from the next point ahead of me or in front of me in terms of x or along the x direction. So that's why the x index only changes from I minus 1 to I plus 1, and j is fixed. So this thing divided by del x squared because I'm taking the derivative with respect to x. Same thing with y. Now in this case I'm changing only the j index, while downstairs I have del y squared because that's derivative with respect to y. Right, so sum of the two terms equals 0. Now the question is, what are the knowns and what are the unknowns? So basically here everything is unknown because I don't know the temperature or anything in the interior. All I know is about the boundary. So we're going to convert this into a matrix. That's the way we do this in direct method. So when you talk about direct method, you have to think about them. At the end of the day, you end up getting a matrix or a system of equation where we have to solve a linear system. So then that's the same thing. So now let's see how we assemble this matrix. To assemble the matrix, you have to go every point from from I equal 1, j equal 1, all the way to I equal n, j equal n. Basically, we're going to go over a grid. So we're going to have a grid on this slab, and we have I index for the x index and j index for the y index, and we go over every I and j, and we apply this, and then we have an equation. We put that equation into matrix. Now, to put that in a matrix, we need to order our unknowns. And the way we order it is, first we're going to fix the I index. So my lower index in I would be 2. Why? Because I equal 1 correspond to x equal x1, which is maybe this edge, which is the west edge. So I know everything along this edge. That means nothing is unknown in here. So that's why t with I index equal 1 does not show up in this unknown list. So my first I index is going to start from 2 because I know everything at I equal 1. That's this edge. Same thing with I equal n, which is the temperature at this edge where I know everything. And similar thing with j equal 1 and j equal n. So basically I, j equal 1 and n do not show up in the unknown list here. That's why I start from 2, 2 all the way to n minus 1, n minus 1. Thinking of I have m discretization along the x and n discretization along the y. So then we have to go over every equation here and ask which of these unknowns contribute to my equation. Like when I put I equal 2 and j equal 2, then I have, you know, t3 comma 2, and then t2 comma 2, then this is going to be t1 comma 2, and then so forth. So then you have to basically fill up this based on the unknowns that you have here. So you have to think about which column would have a non-zero coefficient using this equation for a given I and j. And you're going to start from I equal 2, j equal 2, all the way to I equal, you know, m minus 1 or j equal n minus 1. Alright, so here's the grid that I was talking about. We're going to have n points along the x and n m points along the y. So this is what it is. The way to assemble this is, so we're looking at this, we see that we only have 5 unknowns contributing to every equation. Like these two are the same, so these two would count as one unknown, 2, 3, 4, and 5. So basically for every equation you have to put 5 numbers along every row, but the question is in which column you have to put these 5 numbers. So then you have to go over this loop. This loop tells you at what, for a given I and j, what row and what column contributes to every equation in this matrix. So like I could just go over one of them. Let's say when I is equal to 2 and j is equal to, let's say j is equal to 2 and I is equal to 2, then I'm going to have t22, t32, and t12 from this, and then t23, 22, and 21 from this. So then I put them into this, into these two vectors with the corresponding coefficient. Like the coefficient for I and j, tij, is going to be this. So let's look at this. The coefficient for ij is going to be minus 2 over del x squared and minus 2 over del y squared. And that's why I have, for every combination of I and j, for those 5 terms in the equation, I have the corresponding coefficient. Like for ij, the coefficient is this. For I plus 1 and j, let's look at this. I plus 1 and j, the coefficient is 1 over del x squared. And that's what I have, 1 over del x squared corresponding to I plus 1 and j. Or another example would be for tij minus 1. To go back, tij minus 1, it's this term, the coefficient is 1 over del y squared. And the coefficient is 1 over del y squared in this vector. So I have 3 vectors. One shows the contributing, the I index or the x index of the contributing terms. This is the j index of the contributing terms, and this is the coefficient. Then I have to go back to this matrix and figure out which column I have to put these coefficients. And that's how we can calculate. So this actually gives you the column number. You go to that column, and the row corresponding to that is going to be calculated using this expression. So you know the row number, you know the column number, you go to that A matrix, you put this coefficient in the corresponding row and column element. Now if you ask how I calculate this column and row, actually it's not difficult. You go over rows from left to right, then you go from bottom to top, and then you count like this. So this is going to be mesh point 1, 2, 3, 4, all the way to n, and then you go up, and then there's going to be n plus 1, all the way to 2n, and then 2n plus 1, and 3n, all the way like this. So like for 2, 2, and the matrix you're going to construct is basically containing only the interior points, because all the exterior points are the boundary points, we know the value, so they are not unknown. Alright, so then the element 2, 2 is going to be the first unknown. The element 2, 3 is going to be the second unknown, and so forth. So by this convention, I think if you think about this, you can see that how we can calculate the row and the column for every mesh point. So you assemble the A, and then you have to assemble the B matrix to solve the system. The B matrix is, the way to calculate the B matrix is, you have to go over every boundary point, like go over this boundary point, all the way around this boundary. And then you multiply the corresponding column of A matrix by that boundary value, and then move it to the right side of this equation. So if I know the value for this point, the boundary value for this point, then you multiply this value by the corresponding column of A matrix. So then, let's say if I count these mesh points from, let's say, left to right and bottom to top, then this is going to be the second mesh point. And you go to this matrix and multiply the second column of A by the boundary value at this point and move it to the right side of your equation. And you're going to lower the size of the matrix because you're moving one column to the right side. At the same time, you apply the boundary condition. So your B is going to be now filled. So, and that's what is explained here. So I create a vector where I know the index for the boundary for the mesh points at which we know the boundary value, and the first column of that vector is going to be the boundary value. So boundary value, the corresponding index of from the grid. So from the grid, you know the index, you know the value. Then you create a loop, and then you go over the rows of this vector, and then you ask what is the index of this boundary point, and then what is the value of that. Then you go to the A matrix, you multiply the column corresponding to that index by the B value, you move it to the right side, and say your B is going to be the current B minus the contribution from the A matrix. So you go over all the boundary points like this, and then you calculate the B. Alright, so in the next movie I'm going to show you how to implement the direct method for this heat equation in 2 dimension using central difference. So stay tuned, and thanks so much for watching.